Sometimes a moving object experiences a non-zero interaction with its surroundings during a short time interval, as we show here, or to give another example, as can occur when an object undergoes a collision. Let's discuss how we can start from a fundamental principle to understand and to model motion in a case involving brief but significant interactions. We will use as our starting point Newton's second law, but cast in the form which our textbook calls the momentum principle. We discussed earlier the concept of momentum, where we said for most every problem we will handle in this course, we can take the momentum to just be the product of the object's mass times the object's velocity. The subject of brief interactions is a good place for us to get some practice using the concept of momentum. We also mention here in passing that this form of our fundamental principle is also referred to as the impulse momentum theorem, which in words says the change in momentum is equal to the impulse, which is the product of the net force and the change in time, delta t. Now here's the strategy for using this momentum principle, as we'll call it, for understanding a brief, non-zero, but significant interaction. We can obtain the change in momentum from knowing the object's mass and watching the object move, both before and after the interaction. With that information in hand, we know the net impulse, the product of F net and delta t. So, if we can estimate the time interval, delta t, during which the non-zero interaction occurs, then we can estimate the net force on our object during delta t, the time delta t. Let's use this approach to understand the net interactions in the video we just saw, where a touch on the soccer ball caused the ball's motion to reverse direction. We can analyze the soccer ball using the same ideas that we used earlier when we talked about looking at the soccer ball moving at constant velocity. Here we show the results of this analysis. Doing the analysis on your own would be good practice. To get started with this, you can download the video clip here. Now here's the position versus time plot from Tracker, which suggests that, to a good approximation, the ball moved at two different but constant velocities during two different periods of time, separated by a brief time interval when the velocity changed, and therefore when there was a non-zero net force on the ball due to the surroundings. Now, if we zoom in on this peak during this brief time interval, and we remember that the time interval between adjacent position data points is the time between each video frame, which here is 1/30th of a second, then a case could be made that the interaction started one time interval, that is 1/30th of a second, before the peak, and ended one time interval, that is 1/30th of a second, after the peak. So let's make that assumption here. This means we will take as our estimate for delta t the time interval during which the net force is non-zero. We'll take that time to be 1/15th of a second, roughly a blink of an eye. So that's a brief time interval in everyday life. To apply our fundamental principle here, the momentum principle, to make an estimate of the net force, we're also going to need to know the object's momentum before and after this time interval. To find that, let's first estimate the initial momentum before the peak in our position versus time curve. Let's make that estimate using the two circled positions and corresponding times, where the ordered pair for each point here gives the time in seconds first, followed by the position in meters. Here the points we use correspond to the very first position in time at the start of our analyzed observation, and the point just before the peak in the position versus time plot. Now from this, we can compute the average velocity over the entire time interval and take that as our estimate of v initial. Then with the mass of the soccer ball, we can compute p sub I, the initial momentum. Notice that the direction of the momentum vector is in the plus x direction. This is consistent with our choice of coordinate system, where we choose the plus x axis to point to the right, the direction in which the ball moves initially. Next, we estimate the final momentum after the peak in this plot using basically the same procedure. Again, we use two position versus time points, the two circled points shown, and these correspond to the point just after the peak and in the position versus time plot, and the point at the final observed position in time. From these, we compute the average velocity, the final average velocity, to get v final. Then we can compute the final momentum and obtain the final momentum vector. We're now ready to estimate F net during the time when the ball changes its velocity and therefore changes its momentum. We can calculate the change in momentum, and we have an estimate for delta t, the time during which F net is non-zero. And so we can obtain our estimate for F net, which is 18.1 newtons, pointing in the minus x direction. Now, let's note a few things here. First, if we compare the net force here that we found to the weight of the ball, we see the magnitude of that net force is several times larger than the magnitude of the ball's weight. This is a common feature for brief interactions that can cause a significant change in the motion of an object. Large net forces acting over short times. An extreme example of this can arise, for example, in the collision of an object, where the net force magnitudes can be several tens or hundreds of times larger than the magnitude of the object's weight. Next, it might be tempting to attribute the net force to the interaction of the soccer player's foot with the ball, but that, in my view, would not be justified. The ball is clearly also interacting with the ground. That interaction may change when the soccer player's foot comes into contact with the ball, perhaps the foot pressing down on the ball, pressing the ball into the ground. Our fundamental principle, either in the momentum principle form or Newton's second law, doesn't tell us how to sort this out. All these principles can tell us directly is about the total interaction, however that arises. And even then, in this case, the net force we estimate here is the average during the time interval delta t. This means we're computing F net assuming it is constant in time during the brief time interval delta t. There's nothing in nature that requires this. It could be that the actual F net could be changing in the time during even that brief time interval delta t. To check this, in this situation, would require us to revisit our observations and consider how we might make better, faster measurements. For now, let's go ahead and press on and take a look at using this estimate of F net and see if we can't build a computer model that predicts the motion we observed. We're going to start with the same starter program, lab1start.py, which we used earlier when we discussed the constant velocity motion of the soccer ball. Now, much of what we learned in that earlier example carries directly over. The setup of the graphs and the visualization is identical, so we don't need to change anything here. What we show here is the first place where we need to make changes. We've already put those in. We've put in fact, the initial position and velocity of the soccer ball. And we have the soccer ball's mass. And also, we have the start time for our observation, which we're taking to be t equals 0. Now, notice too that we have for our other initialization the time step delta t. Here we're setting that to be 1/1000th of a second for reasons we'll mention in a moment. Notice this delta t is used for doing calculations in our model and does not have to be the same as the time between frames in our observation video. Now, we need to modify the part of the code that applies Newton's second law to make predictions. Now, as we said earlier, there are really three regions of different motion. So we're going to model each region with its own computational loop applying Newton's second law. First, the first loop will describe the first region of constant velocity motion. Then we'll use a second loop to describe the brief non-zero net force region. And finally, a third loop to handle the second constant velocity region. In all cases, we use Newton's second law with the appropriate net force for each region. Here's the first loop. The initial conditions we set earlier are the correct ones to start the loop off. And notice that we set here, for constant velocity motion, the net force during this part of the motion to be equal to 0. Now, notice too that we are making predictions up until the time of the last observation data point just before the peak in the observed position versus time plot. From here, we then proceed to the second loop, which follows and starts immediately after the first loop finishes. This is the loop where the net force is non-zero, and in fact, we set it to the average net force we estimated earlier. We don't need to do anything to the initial conditions here. The values of the ball's position, velocity, and time calculated at the end of the previous loop, the first loop, serve as the initial conditions for this second loop. We notice too that we make predictions in this loop until we reach the time for the observed data point just after the peak in the observed position versus time plot. The total time over which we make predictions is pretty short, a blink of an eye, as we just said. So it's a good idea to set delta t to something a good bit smaller than 1/15 of a second. So that's why we set delta t to be 0.001 seconds, or 1 millisecond in our model. Finally, we go to the third loop, which starts immediately after the second loop finishes. This is the loop where we once again model constant velocity motion with 0 net force. Again, we don't need to do anything to the initial conditions here. The values of the ball's position, velocity, and time are calculated at the end of the second loop, serve as the initial conditions for this third loop. And moreover, we make predictions until we reach the final observation time. Now, with our code completed, let's go ahead and run it and see what the motion looks like. And what we see is that the simulation, the corresponding position versus time graph, look similar to the motion that we analyzed from the video. We see that the visualized ball moves in the plus x direction, turns around abruptly, and heads back in the minus x direction. Now, let's make a closer comparison of this model, by looking at the plot of the model output versus time and the analyzed observations on the same graph. And here's the result of doing this in the spreadsheet. Here what we show are the observations in blue squares and the model predictions in a solid black line. The model seems to do a pretty good job, but there's always room for improvement.
For example, after the peak in the plot, the prediction does not seem to be as good as before.
In this region, we see that the motion of the predicted motion is over-predicted. It predicts that the ball moves further than what is actually observed, at least at the initial times immediately following the turning point. Now, is this a problem with our model, or our data analysis, or both? Well, let's take a look back at the picture, our video. And in fact, let's look right at the turning point. And remember, right at the peak, we see, and we've said, that there's a non-zero interaction. Now, if we watch and look at the soccer player's foot, what we see is that for the point immediately following, the foot seems to still be in contact. Now, in our model, we said this was where we ended the non-zero interaction. But if we keep stepping forward the frames, we see the foot is still in contact with this frame, and still further, another frame. Now, this raises the question, do we need to revisit how we computed our non-zero net force? For now, we will conclude this lecture without addressing this question here. However, we invite you to explore this a bit, say, by trying different time intervals to estimate the average net force and then trying to see if those new estimates can do a better job of predicting the ball's motion.